Oh, cool. Yeah. Okay, well, we're going to go ahead and get started. So thank you all very much for coming to our first meeting of 2025. So we're a quarter of the way through the century. So lots of exciting things I think are going to happen. We have a full agenda. We start off with kind of Patricia telling us about the latest in space weather. And then we'll have Brooklyn talking about kind of like this once in a, I don't know how long. We'll learn more about it, where all the planets are kind of visible for us to be able to see. And then Greg's going to give us his monthly space news update. So that would be exciting. And then our featured topic is we have Dan here who's going to talk about Europa Clipper. And with that, I know it's going to end in what, depending upon how we have time, we might have Robert talk about the Science and Engineering Fair of Houston, or we might do that at PJ's afterwards. So we'll see how that works out. So with that, let me go ahead and pass it over to Patricia. And let's get your slides up here. Space weather. Yay. And I'll give you this.
Okay. Okay. Space weather update for the past 2 months. Still in solar maximum range because it lasts a long time. It probably peaked, probably, maybe. Let's hope. And this past, between the last meeting and now, we've had 6 X-class flares, and like 100, over 100 M-class flares, and I don't even know how many C-class flares.
That's a lot. Is there a lot of X-class flares for the period of
I mean, not really. Not compared to the last like 12 months. There's been times when we got this in like a week. In May, when I got the pictures in Plannersville, that was off the charts. And in October, when I got the pictures in Plannersville, it was way more active than just this storm. The ones we did have, let me see. We had one December 8th, but then 5 of them we actually had in a short period. And so that was kind of like one storm. Like I consider it one storm because it was just a time of activity. We also had 2 proton events, one that touched the S2 category, one that touched the S1 the one that went up to the S1 category. This one is likely associated with either one of or a mix of these 3 and some of the M flares around that time. Because of the activity that went on around the December 29th, and maybe some of the activity that went on around the 30th, we actually got up to the G5 of geomagnetic storming category level. And that's the highest level we currently have, although this storm wasn't as big as the May or the October storm. And since we got this storm, it gave us some New Year's fireworks. Mother Nature gave us an amazing show. These are some from Alberta, Canada, and these are also some ones from Canada.
And were those all from the same X-class event?
No. It's a combination. I don't remember exactly which. I don't think it was the X1. I think it was something right after the X1 that actually released what caused this. But they all it's not that they pile on top of each other, but they all kind of, you know, when a front moves through the country and there's things it picks up along the way. Sorry, I'm all discombobulated today.
I did have a question. Like X 1.1 versus the X 2.2, is it like just twice as strong, or is it more the logarithm? So it's much.
Yeah, it's kind of like the earthquake scales.
Okay.
So like a magnitude 3.4 earthquake is going to be, it's multiples of 10. Yeah. Yeah, and yeah.
And is it based upon like the amount of material coming out, or like how do they?
The X class is, I'm almost positive, just the X-ray flux.
Oh, the X-ray.
An a solar flare does not necessarily mean a CME.
Okay.
Separate things, but related. Just like there can be, there's usually lightning with rainstorms, but sometimes there can be lightning with snowstorms. Sometimes there can be just random lightning, and that happens too. A lot there. We have had a lot of filament eruptions. So we've had some filaments and prominences launch off, and those add to the solar weather environment. Corneal holes add to the solar weather environment because they add in a lot of solar wind, and that enhances any solar storm that we're going to have.
The blue ones, I guess those are done like X-ray instrument, but then the last one's like this regular visual.
The colors are just different light wavelengths. I forget which colors are which. They're all assigned a number. And so then we got the fireworks, and the storm didn't actually subside until like the 3rd. They were getting really good aurora pictures until like the 3rd or 4th up in Canada. And then to end the talk, I wanted to give you a brief look at the anticipated regions that are incoming. So this is from the Gong Farside viewer. And so it's not an exact picture of what we have on the far side, because I don't think we have an exact picture right now. I know there's one that kind of gives us one sometimes. But these right here, these may be responsible for the activity that I just showed you pictures of. When they rotate around, the sunspots change, but they can survive from one rotation to the next.
Jog our memory. How long is rotation?
27 days.
27 days.
Like
the same as the moon cycle.
Yeah. It's a common time frame. And so with these regions, possibly if they stay active and if they build, when they come on to this side, then we can expect more activity. We can expect an uptick in activity and hopefully more shows. Maybe soon I'll be able to get another picture. For the December 31st storm, I don't have a picture of it, but I did see reports of aurora as far south as the Panhandle, New Mexico, and Arizona. So that it was a G5. So okay, and that's all I have for space weather. Hopefully nothing too exciting happens.
That's awesome. It's amazing. You know, the sun you always just think of is just coming up and going down, but it's doing active stuff too. Oh, cool. And So next, Brooklyn, let's go ahead and move into your topic. And I got this up here. And I think we actually do have access to the microphones now, but we have no microphones. Okay. Okay. Project.
Project? Yeah, just speak, project your voice. This goes on you. Sorry, guys, we're getting used to her public speaking. Okay.
This is the place to practice.
Yeah, it is. So this click.
So that's a laser at the top. And then this is left and right. But we may have to click on the presentation for it to. Okay. Oh, there's like a zoom.
Okay.
Okay. Hello, my name is Brooklyn Levi, and today I'm talking about planets in the night sky. January will be a busy month to look up in the sky. So, 2025 is starting with the Marvelous Planet Parade with one of 6 of the planets in the solar system, including Venus, Mars, Jupiter, Uranus, Neptune, and Saturn, all visible to the human eye. These planets will be available to see up to January 25th. You will need a telescope to see Neptune and Uranus, though. The best time to view the planets is around 8:30 p.m. after sunset. Did you know other planets have longer or shorter hours for their day span? Earth is 24 hours, as we all know. Mars is 24 hours and 36 minutes. Saturn is 10 hours and 33 minutes. Neptune is 16 hours. Venus is 243 days and 26 minutes, which is pretty long. Pluto is 6 days and 6 hours. Jupiter is 9 hours and 55 minutes. Uranus is 17 hours. Mercury is 58 days and 16 hours, or 1,408 hours. The Quadrantid Meteor Show has been active since December 12th through January 12th. How may you see it? Get in a dark area and allow your eyes to adjust for 15 to 20 minutes. This meteor shower is best seen in the northern hemisphere. The moon near Saturn will make a close approach, passing each other. This is a lunar occultation. What is a lunar occultation? A lunar occulation is when the moon passes a asteroid, star, or planet, temporarily blocking it from view. Comet C-2024 G3 will come up within 8.7 million miles of the Sun. This will also be the comet's closest approach to Earth. The Wolf Moon is the next moon on January 13th, 2025 at 5:28 p.m. will appear. What is the Wolf Moon? A Wolf Moon is a full moon that occurs in January. This comes from people saying wolves howl more in winter. On January 16th, 2025, Mars reaches opposition. This means it will rise around sunset, shining bright all night. Mars will be vivid red, making it easy to see with the naked eye. Venus will be at its greatest elongation on January 10th, 2025. This means Venus will be the farthest from the Sun in the evening sky. Okay. Thank you for all listening to my presentation all about cool things happening in Earth's sky in January. Make sure to look up in the sky and join us on February 8th, where I will be speaking about Black History Month in space. Oh, yeah. Let me take this off. I do not know how to take this off. You got it?
Yep.
Thank you.
Awesome. And then next up, oh, wow. What happened there? Oh, it is the end of the slide. It's supposed to do that. And then next we have Greg with the monthly space news. Let's see. I think this is it. And I'll go ahead and get you set it up.
All right.
And I'll click on it.
Okay, I've got
Oh,
this
you
here.
got one. Well, you
I
want
need,
to?
I need to turn the mic on.
Oh, we could just trade.
No, I got it. There we go. Okay.
Now I have to figure out how to turn this off.
Just hold the button in for a little bit. And where's the clicker?
Oh, I took it away from you.
Okay. All right. So normally we do monthly space news. This time we'll kind of do a really quick review of what happened in 2024 and a look ahead at what's coming up in 2025 and a little bit beyond. Obviously, that mishmash of pictures up there reflects things we've talked about during the year in the past. So let's do, first of all, space by the numbers. What happened in 2024? We got a table here. Your eyes may glaze over, but the important thing is that last column for 2024 showing what countries launched how many different rockets, and pretty much going by the first stage, who owned it, who made it. And so the U.S. here is the leader. What that really means is SpaceX is what it comes down to. It's mostly SpaceX.
Should we give a shout out like, yay?
Yeah, go USA. Yeah, there we go. Okay. But, actually China's held kind of constant, but they're, in general, they are working very hard to catch up. And they are going to start launching a whole lot of constellation satellites for communications, 2 different complete ones, the 10,000 satellite kinds of things. So they will be starting to catch up. Their problem is they have yet to master the fast tempo that the SpaceX can do of launching every couple of days. They haven't gotten to that point yet. But third down, and notice these are ranked in order actually by either the number of successes, which is the first number there, or the second numbers, which are the number of launch attempts. So usually they're pretty close, but everybody has a failure now and then. Even SpaceX had a couple of failures this year. So third is Russia at 17, Japan 5, India at 5 also, Iran at 4, which is ahead of Europe. I mean, that's kind of it's sort of sad how far Europe has fallen. The entire continent of Europe, is only, but some of that's kind of a fluke in that they're kind of in between generations of rockets. They had pretty much stopped production of their old ones, and they hadn't actually built their new ones yet. So there's new ones coming online this year, so that will help them quite a bit. And then the oddballs, North Korea, South Korea, Israel didn't have much of anything. But what's interesting is the trends here. If you look at 2021 to 23 or 2022 to 24, basically we're doubling every 2 years. That seems to be how that's going. Now, this is in terms of number of launches. There's different ways of measuring success. But before I get to that, I should get down to my footnotes down there. So our count there did not include the Starship test. There's 4 of those during this year because they didn't really go orbital. This is really how many rockets achieved orbit or beyond, going to the moon or some other planet. SpaceX accounted for most of that. When you get down to it, the 133 out of the 155 launches or successes. And
brief historical perspective before we move on.
Yeah.
Yeah, around 2000, and that SpaceX got started in 2002. Around the year 2000, the U.S. numbers were in around 12 to 16 launches a year, and that was pretty good compared to China, which had almost no launches, and Russia, which had usually 2/3 of that rate. So
yeah, Russia's been pretty constant over all the years.
We've gone from a dozen launches a year, 1 a month, or 1.5 a month, to these numbers.
Yeah, and of course, most of that reflects communication satellite constellations. I mean, Starlink in particular, being a vast part of that.
I've got a question about your chart.
Yeah.
Should we eventually start separating your chart showing SpaceX different from U.S.?
Well, that's why I just kind of put that in the footnotes. That's
I just wondered,
yeah,
because a lot of the American launches are all SpaceX launches, aren't they?
Yeah, but coming up, Blue Origin will probably finally come online this year, and there's going to be some launches from the others, Vulcan and those sort of things, and technologically they're way behind, but nonetheless they'll get a lot of business just because SpaceX can't do it all, or those companies don't want to give money to SpaceX. So either way,
I was just thinking as they go forward, it's going to become an issue if SpaceX starts launching a lot of bigger launches, independent of the American, NASA program.
Oh, well, it is independent now. Well, most of it's for their own purposes because it's Starlink, which is communication satellites. That's for them. That's not really for the U.S. particularly. But that's true. Commercial, and that's actually one of my trends I'll get to later. The commercial launches are what dominates now. It's not military anymore, and it's not prestige. It comes down to, things like communication satellites or Earth observation satellites, where you monitor what's going on all over the world, and that's really where the business is going these days. So yeah. Anyway, so the Starlink is a big part of that, but other constellations will be starting up. In particular, Amazon's Kuiper project, and they're going to actually have a couple token launches on SpaceX, but not much. They don't want to do that. They're basically funding all the other competitors right now. If it weren't for the Project Kuiper, they would just be dead, essentially. Even though they haven't started yet, but they've signed contracts to launch quite a few. Okay, but there's another way to measure, and that's mass to orbit. You can talk about launches, but then there's a lot of launches like the Electron rockets from Rocket Lab. They're pretty small. They don't really launch a whole lot. You start looking at the mass to orbit. It's like, SpaceX is up there, at 1.5 million kilograms. The next one is China. They're down there at like 62. It's like a factor of 20. Now, in the case of China, they don't really report a lot of their launches or what they're really launching. So that's why, where I pulled this number from, they also indicated how much was actually reported. In this case, China only owned up to essentially 20%. So you can't, you can say that probably they launched quite a few more tons, than shown here, but you still kind of get the idea that most of the mass that's going up there is, again, being done by SpaceX. It's SpaceX in terms of launches is already more than half. Basically there's more launches from SpaceX than the rest of the world combined by number of launches. And the same is true for mass, even more so.
But if you, and so that 62,000 kilograms is that 18% reported?
Yeah,
And
they've only reported that much, so you don't know about the rest. So,
you don't know about the rest,
but it might be 5 times as much, for instance, as an example, maybe.
300,000 milligrams of a kilogram.
Well, yeah, I wouldn't worry about the milligram satellites too much. Yeah.
But and then for us though, so I mean, if you extrapolate it out, then China would have more mass to orbit.
No, even if they had 5 times as much, that still only puts them at 300,000.
Oh, that's 300,000. Okay,
Yeah.
Great.
So
Excellent.
anyway, they're up there. There's some Russians there. MHI is Mitsubishi Heavy Industries out of Japan. India is coming along. They report everything. The ISRO is the Indian Space Research Organization, or whatever it is. Okay, other things to look at here. I decided to start keeping track of this because most of the growth in all these launches has been for low Earth orbit, because of Starlink, communication satellites and so on. It turns out I found actually Wikipedia reports this, so I just basically took their numbers. I didn't take anything before 2023 because their total launches didn't match up with anybody else's, so I just sort of gave up on that. But these are consistent with total numbers of launches that everybody pretty much agrees to. And they categorize them this way, starting with, transatmospheric. What that means is ones that actually, maybe they go around the Earth once or twice, but they dip into the atmosphere so far that the friction the friction slows it down and they don't last very long. And usually that's by accident. That happened with SpaceX. They had a second stage that didn't do what it was supposed to do, and they lost a whole batch of satellites as a result of that. Sometimes they might be tests, like if they're testing a space plane or something, you have that. Most of the growth, though, even in 2023 to 24, is in the low Earth orbit and sun synchronous, which is a special case of low Earth orbit, meaning, it's not up there too high, but it also has some special characteristics of it's in the same place in the sky every day, that kind of thing. The next one up is the high ones, which are the traditional ones, the geosynchronous satellites. They're the ones that typically go in an orbit around the equator or close to it, very, very high up, the 25,000 mile kind of category. Those are where, for instance, almost all the old spy satellites and communication satellites were and still are, but that's been holding steady for decades now. They've been, those orbits, especially the ones around the equator, that's pretty much filled up at this point, even though it's way, way out there. There's variations on that. So geosynchronous means basically a big circular orbit. But a lot of times what happens is you see somebody does a launch and they're launching a satellite which is going to end up in a geosynchronous orbit, but the rocket doesn't take it that far. The rocket really takes it to an elliptical orbit that's really coming down all the way to low Earth level, and it's a transfer orbit which will also take it up, but it won't stay that way. Then they have to circularize the orbit, meaning they apply thrust, like with an ion engine. It's very, very low thrust, but they apply it for 6 months or something, and it eventually works its way up. And that's actually an awful lot of the satellites get launched that way. They don't really very often go all the way up to being a geosynchronous high-level circular orbit. Tundra is just a giant elliptical orbit, kind of that's used typically by the Russians if you want to hover over an area like the very, around the North Pole. The geosynchronous satellites can't really do that because they're based around the equator. So they have different orbits they go for. Medium Earth orbit, there's some communication satellites there. The GPS satellites are there. And so there's been kind of a steady but not growing population of that. High Earth or lunar transfer, these are typically lunar missions. There have been a few of those. And then, of course, the ones that are going even farther. Heliocentric just means you're basically going orbit around the sun, which everything we've done so far, maybe except Voyagers, has pretty much been that. So what's the main thing that you want to track is the growth is still in the low Earth orbit area. That's the area that's the most crowded. And of course, it's being closest to Earth, there's also less space there.
Heliocentric. Really, those are all science satellites.
Yes.
They're mostly NASA or
Yeah. No, eventually, when you send people to Mars, I mean, well, that'll become as a planetary transfer. So, those will be changing over time. Okay, now in terms of qualitatively, the highlights, what sort of things happened in 2024? Well, one we already talked about it here. SpaceX is kind of dominating everything, basically launching more than the rest of the world combined by launches or by payload mass, either way. Now, and of course, there's a reason for that. They deserved it because they got the costs down because they focused on cost, which nobody else did. And in particular, when they went for reusability. And most of what I'm calling the competitors, like the Europeans and the Japanese, they were still targeting making something as good as the Falcon 9 was in 2010. Okay, they're that far behind. I mean, they just came out with the Vulcan, which is pretty much like that. The Mitsubishi H3 is pretty much like that. The Ariane 6, pretty much like that. All those things that everybody else was building are just already way, way behind. Starting around 2017, that's when a lot of these, giant the giant constellations got going. That's mainly because of reusability. It just made it possible to launch a lot more often. And a lot more cheaply. But the next thing, of course, is simply that because of Starship, its testing at this point has pretty much convinced everybody that it will succeed. I mean, obviously, there's a lot of things they still have to do. But all those nagging doubts that were on there earlier that, they'll never be able to do reusability with a large, heavy lift vehicle or this or that, that's all pretty much fallen. Everybody's kind of given up on that. All that trash talk is pretty much over. And the other thing, though, of course, with them, we talked about this in one of the previous meetings, is their launch revenue is important, but it's not as big anymore as the satellite-based revenue, which they're getting from Starlink. Their internet service is actually now funding, everything they do. And they have about 6,800 satellites up there, 6,800 some. That was as of January 8th. So those pictures there are just kind of reminders on what their businesses are. Falcon 9, because of the reusability, frequently lands on an ocean-based platform, or it might return all the way to the launch site. Starship testing, they actually are, they're catching with these mechanical chopstick arms. That's a picture of the booster coming back. And that's just a reminder of on the right-hand side is a reminder of the satellite business essentially filling the sky. Now, in reality, the sky is not filled up as much as it looks like there. That's just phase one with 1,500 satellites. But no satellite there would be as big as 1 pixel, which is, you look at this and you think, oh my gosh, there's no room left. There's still a lot of room left up there. Okay, more space highlights. The big theme here is commercial activity is increasing in a lot of ways. And this even is affecting the military. I mean, it showed up, for instance, in the Ukraine war, where right away the people in Ukraine started realizing, they can use Starlink for their own purposes, for communications and for navigation and everything else. You see it, in the old days, the military, for instance, the spy satellites, there were big ones, they were up in geosynchronous orbit, they were over $1 billion a satellite, often a lot more than that even, up there way high. And they suddenly realized now that those things are just big, juicy targets. It's too risky to put all your money in just a couple of giant satellites. And so now already, people don't realize it, but already the U.S., for instance, they have a constellation of about 100 low Earth orbit satellites doing a lot of the same stuff for monitoring. And that's for, monitoring, what's going on with people's militaries, monitoring for, nuclear explosion, takeoff of rockets that might be ballistic missiles, that kind of stuff. So Starlink, of course, is the big private satellite constellation, but there's a whole bunch of others coming along, including China's and Amazon's. Now, what's new is that private companies are now landing on the moon. Now, of course, companies always built these things, under government contracts. But what's different is now the governments are just buying the service. It's like they are now a trucking service, and you're buying the service to get you in a big truck to get to the moon. And so at least there have been 2 soft landings in the case of Intuitive Machines and iSpace. That's a Japanese company. I'll get to those in a minute later. We also had the first commercial spacewalk. That's the one picture on the bottom left over there. The space station plans that are being done for commercial space stations, they're firming up. Actually, Axiom says they're going to launch their first small one in 2025. That one kind of surprised me. I hadn't realized they were that far along. VAST is another one. They always talked about having artificial gravity in their stations. They're looking at putting up something. It won't be up that early, maybe 2028, but that'll just be a single module. It'll be something that later on will fit together in a bigger station, but they're getting something up there. And the other thing that was really getting obvious this year is space manufacturing is starting to look like it might actually happen. Varda in particular, we talked about earlier in the year, the upper right-hand picture there, that little satellite there, inside of that, they have a miniature factory. They were making drugs, very high-value drugs. It turns out in microgravity, they can make much better quality ones. And there's similar things going on with fiber optic cable from Philips Photonics. Redwire is doing a bunch of stuff with pharmaceuticals also. Airbus was doing some stuff with metal 3D printing in space. So a lot of this stuff is coming along. It's starting to look like it'll really happen. Okay, next thing on highlights is lunar landings. Again, this has really picked up. We really are going back to the moon, hopefully to stay. It remains to be seen. But now some of that's China. I mean, China has really come through strongly here. They've actually returned samples from the far side of the moon. I mean, this is something the U.S. has never done. They're way ahead of us on that. We know how to do it on Mars, but we've never actually done it somewhere as close as the moon. They put up some lunar communication satellites, communications relay satellites to do that. If you're going to have something on the far side of the moon, you can't talk to it because the moon blocks it. So you have to have a satellite up there to pass it on. And we had the 2 soft landings. Japan's Slim Lander and Intuitive Machines had Odysseus. Now, the only bad part was they landed and they kind of tipped. You see the bottom pictures there. So the only ones that actually landed upright was a Chinese one on the far side. And previous times they had done it on their side as well. That's the Japanese one there in the middle on the bottom. It landed and it kind of rolled, but they still got some things done. So they called it it was at least a partial success, not a complete one. And the Intuitive Machines one, the same kind of thing happened to it. It landed, but it tipped.
Did India have a lander?
They did. I'm trying to remember why I didn't include it. I think that was the previous year. I think that was 2023. Yeah. Actually, so they've been doing this too. And it's easy to forget, but India is becoming a major space power. And that is an interest of theirs.
And they even announced their first set of astronauts.
Yeah. And that's actually one thing I didn't get into the slide. I probably really should have. They're doing that. Okay. Now, in terms of deep space kind of stuff, there were 2 big ones, and you're going to hear more about the NASA Clipper one a little bit later in today. But NASA's launched the Europa Clipper, which is Europa is a moon of Jupiter, and there's a lot of interesting reasons why you want to do that, and we talked about that. And the other one is the European Space Agency did launch the Hera mission. That was launched on a Falcon 9, US. But anyway, they launched that. That's the follow-up. NASA had done this DART mission to prove that if we could blast our way into an asteroid, we could change its position. So if it were coming in and we're going to crash into Earth, we might be able to divert it. It was kind of a test of can we even do that kind of thing. And so we did that, and it looked like it was pretty successful, but they're sending a follow-up mission to go back and take a good look and figure out what really happens. The problem is it's far enough away that you can't really see it very well. I mean, even with things like the Hubble telescope, you can't really make it out that well. So those are major highlights in terms of deep space kind of missions. Okay, some things that are coming up. So this is 2025 now and beyond. One big one coming up is Starship. I mean, this is still, despite everything I said about, the Falcon 9 already is kind of dominating space. this is really appears to be the real future of space. And this is a factor of 10 or more cheaper to get stuff to orbit. I mean, it's that much of a difference. So this is the single most important rocket program going on right now. And that's being test number 7. They're still doing only suborbital tests. That's coming to an end pretty soon. But for a variety of reasons, one of which is they don't need to do any more than that. They're still trying to prove out basically launching or returning back to the launch site, that sort of thing. They're still using the Raptor 2 engines. They have Raptor 3s coming along, and they've built them. They're much, much more efficient, so much, much more powerful and efficient, and that'll increase the capacity of this thing even more. They're not using those yet. So in terms of what they're doing in this test, the Super Heavy booster, first of all, they're coming back to the launch site like they did in test 5. That's their plan. One thing they're doing that's different is they are reusing one Raptor engine. They didn't have that. They haven't done that before. Their whole goal is to make the whole thing reusable. But so they're at least doing, well, okay, well, let's at least do the engine. You know, so they're starting with one. And obviously during the year, they'll do a lot more. Yeah.
You gotta know that the first time I heard that they wanted to return the booster to the pad, I thought the kids got on.
Everybody thought they were crazy. Yeah. Actually, there were people in SpaceX that thought that was crazy. And when Musk pushed it, and it turned out he was right. Yeah. Yeah.
Double positive.
Yeah.
Think outside the box, but indeed a mile away.
Yeah.
The box.
Yeah. And I'll say some of that is also a tribute to the fact that the people that do the controls to do this stuff are just really good at their job. And they have the best, they obviously have the best in the world right there. So the tower also had some changes. In particular, in test 6, they ended up not bringing the booster all the way back to the landing site. They had some problems and it got flagged. Some of those problems apparently were related to sensors on the tower that weren't working. Now that includes radar, which they've now upgraded. I don't know if what else they were sensing, but the radar mainly was used to figure out the position. They want to know within about a half a centimeter where that booster is. And this is a giant booster coming in, still pretty fast, pretty heavy. They need pretty precise landing, and they're doing whatever they can to make sure that works well. So as far as the upper stage, that's where a lot of the real interesting stuff is happening right now. The upper stage, which is what they call SHIP or Starship, that one is now, it's actually a whole new version. It's called Block 2. The aerospace industry, they make up these words Block 2. You see that kind of thing all the time. I don't think anybody else does that except aerospace. But anyway, Block 2, it's version 2 is all that means. And they are testing out a new one. For one thing, it's taller. It's 6 feet higher, so they've added more fuel tank capacity. Most of that went to that. They also actually took a little bit of the payload volume out. They rearranged it so they could squeeze in more payload, actually. But in terms of the thing is taller, but some of that was at the expense of payload space. But there are some changes. The flap design, the forward flaps, they're the things that allow it to coast down and do it under control so they can stay at a particular orientation, in particular keeping the bottom facing the Earth, because that's the part that heats up. They don't want to flip it over. There's no tiles on the top. So they need to do that pretty carefully. So they finally come up with a new flap design. It sounds like pretty minor and technical, but actually it's the key to the whole thing really working right. New avionics, thermal protection, that's still the biggest issue. You can it's suggested in this picture on the bottom here. That's sort of what it looks like when the stage 2 is coming down to Earth. It's relying on getting very, very hot, and that slows it down. But obviously, if it burns through, then you lose it, you can't reuse it. So they have to worry about that. They've also done some stuff like that wasn't really clear at first why they're doing it, and they haven't really said much about it, but they have propellant lines inside the spacecraft, and they're vacuum jacketing in them, meaning they're putting those lines inside of a second pipe, and you could probably think of it as being kind of like a Dewar flask or something, a vacuum flask, basically. That is better insulation. I suppose it also actually helps if there's ever a leak, it'll actually catch that. So there's several benefits to that. One thing they're doing here is lighting up an engine in space. They're doing that as part of their test. They need that for they did it in flight test 6, but they need to keep doing it. That's a fairly important one. One reason is that once you're up in orbit, you want to be able to say, okay, it's time to come out of orbit. You got to be able to restart your engines to slow down to come out of orbit. The second thing is, ultimately, Starship's going to be a variation of Starship will be used for landing on the moon. And you want to make sure you can start your engines up again. You know, when you're sitting there on the moon, very cold, you know, you don't want to say, oh, darn, I can't get this thing started. So, you know, you have to work on that. One thing they're doing that's new is they're finally going to do some payload deployment tests. They haven't done that before. So they're going to simulate having 10 of their newer generation Starlink satellites. They can't launch these yet. They have the V2 Mini, is which they're launching now. But they really want to launch these ones that are much bigger and heavier. They can't do it on a Falcon 9. They need to use this. And this is actually extremely important for them because they want to get going with getting their bigger satellites up there so they can get more capacity on their network. And then there's a variety of things they're doing. They're testing out. They haven't actually, you know how in the first stage, they have these little pins that come out so that when the booster drops down, it gets caught in those chopstick arms. Well, they don't have those on the upper stage yet because they're afraid they'll burn off. You know, because all that extra heat you're getting, you're coming in a whole lot faster from higher in the atmosphere, and so the temperatures get much higher on the upper stage. So they're worried about that, and so they're trying to put some in now just to see what'll happen. They're saying it's non-structural, meaning you couldn't actually land with them; it wouldn't support the weight. But at least they want to find out, you know, will they melt off or not? You know, so they need to experiment with that.
I saw something about them actually retracting and deploying those pins.
That part I don't know about. Could be.
Ultimately, they may end up having.
Yeah, and I think that's the kind of stuff they're experimenting with. They need to figure that out and this is why they're not catching the second stage yet. Because it comes in so much hotter that you know things like little pins sticking out aren't an easy thing to keep in place. They're also on purpose going to have a steeper reentry profile. They want to basically really stress this thing to make sure that they can control it, you know, even under very adverse circumstances. So they're actually purposely going to make this thing get as stressed as possible. Okay, other launches coming along. Blue Origin, you know, this has been on my chart of upcoming launches now for quite a while. You know, now I think is really just weather. They actually want to land their booster on a barge out in the ocean, and the weather was pretty bad out in the ocean. So they put it off, but it's coming very, very soon here, you know, possibly tomorrow. You know, it's, you know, very, very soon. They said this landing their booster on a barge is a bit of a stretch goal. They don't know if they really can do it, but they're going to give it a try. They are going ahead and putting a big payload simulator in there, 45,000 pounds. That's pretty substantial. Even the Starship earlier test, they didn't really have much of a payload at all. I think because the engines were still pretty new, they weren't really sure they were getting enough power out of them. They weren't taking any chances. But now, I guess Blue Origin is now confident enough in their engines, they're willing to actually do that. Now, they're not going to launch that payload into anything. It's just going to be stuck on the upper stage, and the whole thing will just come down together. We talked about the Starship flight test. There's a whole bunch of lunar landers coming along, again, this coming week. We're talking not distant future. We're talking, you know, like a few days from now. There's two of them, one from Firefly Aerospace and one from iSpace Japan. They're actually going up on the same Falcon 9 rocket. They're being, you might say they're competitive, but they're both going up on the same rocket. And that'll probably be January 15th. Now, usually they say no earlier than, so, you know, it might actually be later than that, which is kind of funny. That's another thing the aerospace business does that's kind of weird. Normal project management, you worry about the latest possible time you can launch something, and that's usually your goal, is to make that as early as possible. Aerospace it's always the other way. We're not going to do anything any earlier than this or that. You know, that way they're never wrong, I guess is part of it. Okay, Rocket Lab, we talked about this last time. They're sending a private mission to Venus to look for evidence of former life on Venus on one of their Electron rockets, which is even a small rocket. It just goes to show you can do a lot in a small rocket if you really work it pretty hard. And by the way, that upper stage is doing that. It's from the Electron. It's called Photon. They're using that for lunar missions. They're using that. There's a couple satellites going to Mars. They're using that Photon thing as well. So Rocket Lab, although they're kind of the second most popular launch, they're still having trouble competing against SpaceX. But the way they've addressed that is they're doing all this other stuff, you know, like having spacecraft that are going into deep space, even small ones, and that's how they're keeping in business. Intuitive Machines will be launching in February, so there's a whole bunch of lunar landers coming along very, very soon. Then the big one's coming along, Amazon's Project Kuiper. That's another one that's been put off kind of forever, but they're finally saying their first operational launch will be this quarter sometime. So we'll see. That'll be on an Atlas V. they don't have, their own rockets aren't really ready for that yet, so we'll have that. Axiom's doing another private mission, going to the space station. The Dream Chaser space plane. This is, space plane is kind of like a space shuttle kind of a thing where it can land, it's just for cargo. They were hoping eventually it could be for people, but it's just for cargo. They're targeting May for that now, so that appears to be on. Now these Mars satellites, there's a couple of satellites to go up around Mars. That originally was going to be, what was that going to be on? Something or other, and then that fell through, and they were going to be on the very first Blue Origin test launch, but then that missed some kind of a launch window. So now they're finally talking about launching something in June. Neutron, this is Rocket Lab's attempt to compete with the Falcon 9, meaning reusable. It is a methane-fueled rocket, so in that sense, it's more modern. It's more like the more modern rockets. That's coming up in July. Another lunar lander from Astrobotic. Remember, their first mission failed, not because the lander failed, but actually it was the spacecraft on the way over. They had a valve problem. They had to bring the thing back to Earth. And then Intuitive Machines will be doing another one. Space stations, I mentioned that one briefly. VAST is coming along. In 2025, they claim they're going to launch something. Now, this is not one that has artificial gravity, spinning to, give you gravity. This is really just going to be one, kind of like the existing space station. But the plan is they'll be able to start assembling that into a larger system, and at some point, they want to have artificial gravity. That's, you view that as, how are you going to live in space? Well, it's not really healthy for people to live in microgravity. It just doesn't work that well. So, at some point, someone has to test this out. And it's amazing we've gone as far as we have. Nobody really knows how much gravity you need to survive in space. It's just not been tested. Of course, it means you got to have people to do it. But we've been doing it on the space station, and what we know is that you can ameliorate some of the problems, but still, it's pretty serious. Okay, now Axiom has a competing space station, and they just revised their plans in December. Originally, they were going to just put up a habitation module and rely on the existing power and air and all that kind of stuff, life support, from the existing space station. The problem is they were going to go to a port on the space station that now has been reserved for the SpaceX craft that's going to go up and deorbit the thing and destroy it. Okay, so NASA said, we need that, so you can't have that anymore. So they revised it, and now what they're going to do is they're going to send something up that's actually a power module, power and life support. They're going to send that first. They'll attach to a different place, just where a normal cargo ship would go. And then their next one, which they'll send up, and that's in 2027. And then in 2028, they're going to send up the habitat. At that point, they'll decouple from the ISS, and it'll be self-contained right at that point. So actually, this says 2 years earlier than their original plans, they'll have something out there. So that's where they stand right now. Yeah.
So just to clarify, I'm not like you guys, but so Axiom's going to have their own space station.
Yeah. Yeah.
And it's not going to be, but it will be in the same as our space station.
Yeah, it will be. They'll be pushing off, from it. So, the VAST will be a totally separate space station as well. Well, there's VAST, there's Axiom, and there's a joint venture with Blue Origin, the thing called a Coral Reef or whatever the heck it is. So there's at least 3 projects underway. Now, which ones will actually happen, who knows? But these two seem the most likely to get going, except for the fact that Axiom is in financial trouble. We talked about that last time. So there's a whole separate issue there that they may or may not actually make it that far. But assuming they do, they'll do it. What's interesting is, so Axiom, they actually subcontract out the building of the actual vessel, pressure vessel itself. There's an Italian company that's doing that. And they just sent them orders saying, well, okay, you're no longer making the human habitat, now you're making the power module. And it turns out they fit it in pretty much the same space. So it was well working out.
Autobots, I think. Airbots, I'm sorry. Now.
Oh, no, it's not Air. No, this is Thales. Yeah. I don't know how to even pronounce it. I was guessing Thales, but yeah. Yeah, they've been doing a lot of that stuff, for Axiom in particular. Okay, then you get much more speculative when you go out a little further here. The Starship at some point, as part of its contracting with NASA, they have to do a demo just to show that they can go to the moon and land there. No people involved, and they were talking about doing that in 2025, and that just seems very, very unlikely at this point. But maybe 2026, who knows? But of course, the big, it's more of a political question at this point. But what's going to happen with Artemis? Is Artemis as it exists now, based on SLS, still going to survive? We don't know. But the current plans would be 2026 would be the crew journey around the moon, not landing, just going past it. And then Artemis 3 would be in 2027. I put question marks there because this is all going to be up in the air, remains to be seen. Now, in the meantime, SpaceX all on their own wants to send some starships to Mars, assuming that they're in good enough shape. And again, no people. This is just to show, you look at it this way, how do you do testing, on going to Mars? You can only do it every couple of years because the launch windows, the planet's lining up the right way. So you might as well send a whole bunch of ships, and try landing one, and if that doesn't work, change the software and do something different. My guess is that's probably what they would do. They would actually have some incentive to do that if the Starship is far enough along, and it may or may not be, but they've talked about doing that anyway. One of the Indian missions coming up, they're doing lunar sample return missions also. They've got one planned for 2027. And what I should have really included on here is they have a manned space station, kind of program going on as well. And as you mentioned, they've already selected astronauts for it. They've got the plans going. Now, the only one you can probably really count on is China. Actually, they've been hitting basically every other year. They have a major milestone. They've got a couple more lunar landers coming, but they're getting more and more sophisticated. And they're going to be setting up stuff in 2026 and 2028, and getting ready for a crewed mission in 2030. And they've been on schedule. When they say they're going to do it, they probably will. So they could easily beat the U.S. if we don't. Anyway, yeah. well, how many hours do you have?
I'm just wondering, like, what is the holdup?
Yeah, well, it's just the problem is, in some ways, there's so many answers to that. I mean, it has a lot to do with how they're funded. They were basically directed to use old hardware. I mean, pretty much the existing stuff is pretty much based on Space Shuttle. They're using the same engines, literally. Even
That's the Senate launch system.
Yeah, it's called the Senate Launch System. So NASA's hands are tied to a certain extent. They weren't really even allowed to develop new technology. But then again, they were kind of willing and complicit in doing this too, because they just saw that as well. That allows us to keep going. We get political. It's more of a political question than anything else. But the net result has been there's been a lot of money spent and very little actual results. So, and because that wasn't the goal, a lot of what that stuff is kind of a jobs program. This is personal opinion here, but it's shared by a lot of people.
Also sure you could still spend the bucks and still not end up with bucks.
Well, that's right. Yeah. So you could just say the money was not spent wisely. I mean, for instance, you have SLS. Now it appears it costs about $4 billion to do one launch of that. The entire budget for NASA is like $25 billion. So you do a couple launches of SLS, you chewed up a major part of the budget, and that's pretty much a boondoggle. I mean, it's pretty much at this point, it's gotten obvious that is not the future direction for how we're going to get to space. It's not for no other reason than it's way too expensive. You're never going to have a sustainable space program based on space launches that cost $4 billion. It's just not practical. So, well, I'm afraid I didn't really answer it, but it comes down to it's bureaucracy and goals that don't really necessarily match up with the technical aspects very well.
That's a little more cautious than
Yeah. Okay, actually, that's it.
SpaceX try to go to the moon?
SpaceX is trying.
They are. Well, yeah, they're a part of the Artemis program. Actually, it's a very complicated scheme where they keep all the existing parts, plus they throw in a Starship to go. They have a Starship to go up and pick up some astronauts, and then drop them down to the moon, and then take them back, and then the Orion capsule brings them back to Earth. And it's a very elaborate, complicated scheme, mostly because they were directed to try to reuse as much stuff from previous programs as possible. I mean, a lot of people would say that. But, well, NASA needs a shaking up. Yeah. Yeah.
Get the vote. Don't change anything. Congress passed the law saying you go back to the moon. You got to use. They passed a law. if you try and make something new, and that's if I make something new, they could go to jail. Okay, so that's kind of what a major part of the problem. Yeah, so then Congress pushed back 100%. Exactly.
We would have been ready for what the Constellation program.
You did continuity. Yeah, you can't do a stop, stop, stop.
Well, and that's a whole other issue, and that tends to happen. Anyway, I guess that's it.
I guess that was the discussion right there.
Yeah, I mean, yeah. Okay.
Gateway.
Well, to me, they're all, Orion, Gateway, and SLS are all in the same basket of dustbin of history kind of candidates. They were designed for a different era to create jobs and not related to being efficient and going to the moon or anywhere else. But that's more personal opinion. Okay. Yeah. Okay, so now we're ready for the main talk here. Okay.
Restart at the beginning,
So, what?
which is in the middle.
Yeah. Okay, so, sorry. Well, okay, we'll get back to, there we go. So I'll turn this over. I don't have a slide to introduce Daniel Roy. Christian, because he's been giving lots of talks here. Dan is, I don't know how you're splitting this up even, but, I see both their names.
I'm just sitting here rooting for him.
Oh, okay. So, well, Dan, I guess you're on.
Okay.
So you have this. Here, let me give you a microphone. So the actual microphone.
Watching this?
Yeah.
Right here.
Oh, cool.
So, yeah, the microphone part is on the top here.
All right. Good.
You may become an internet sensation.
Do you have some subtitles you can put to explain what it is I'm talking about? That's okay. Christian, you will do the ultimate translation in German. Okay, that will be perfect. Okay, I apologize for my accent, but I'm from Paris, France. I have a double degree in biomedical electronics, and then I got my MSCS. I worked for 12 years at the Goddard Space Flight Center, the best 12 years of my life. And then I went to the DoD. The DoD noticed me and shipped me to Pittsburgh, PA, at the Software Engineering Institute, where I spent another 6 years. And after that, I had customers at NASA, I had customers at DoD, I had friends everywhere. I started my own company. And that's where I really made my money. All right, so I want to tell you about this wonderful mission. But first, I want to explain my gratitude to you, Nathan, because you have put together a wonderful chapter of NSS. Absolutely wonderful. And all of us in this room, and all of us watching, certainly all of us at NSS dream of a future. Well, last night I had a little dream. I thought that I was in October 7, 2040, 2040. October 7, 2040, I was in the beautiful concert hall of Stockholm when the kings of Sweden were awarding the Nobel Prize for physiology or medicine to Boni Buratti of NASA JPL and Olivier Wittners for our European Space Agency for the stupendous discovery of life on Europa that had happened 10 years before. Now, if you think 10 years is pretty fast for a Nobel Prize, I remind you that Jennifer Doudna and Emmanuel Charpentier got their Nobel Prize for CRISPR in 2020 for a paper published in 2012, 8 years later. So it can go pretty fast when you have such incredible results. Now, if we were to indeed have this kind of finding, it would be absolutely extraordinary. But back to the 2020s, let's have a look at how it really started.
The most exciting thing about Europa can be summarized in one word: water. Now think about all the water on Earth and double that. That's what we think is on Europa.
We need to go there to explore it, to understand, is this place a habitable environment that could potentially support life?
Getting close to Europa is a huge challenge. It sits in the worst possible radiation environment, trapped by Jupiter.
Europa is a moon of Jupiter, about the size of Earth's moon, which has an icy surface that probably hides a subsurface ocean.
Scientists think Europa has the key ingredients to support life as we know it. Number 1, water. Number 2, energy. And 3, essential chemical building blocks. For the first time ever, we're sending a spacecraft completely dedicated to studying this moon.
The 3 main things that we're going to explore at Europa are the ice and the ocean, and understand that intersection between the two, study the chemical composition of the moon, as well as the geology and whether it's active currently.
Europa Clipper is not specifically a life search mission. We're going to understand the potential habitability of Europa. The spacecraft has 9 instruments and a gravity science investigation. 5 of the instruments are called remote sensing instruments because they measure light reflected off Europa, like a camera or a spectrometer. The other 4 instruments are measuring the environment around them, like sniffing gases or dust.
Europa Clipper is the largest spacecraft NASA has ever built for a planetary mission.
It weighs 13,000 pounds, 6.5 tons. That's like the size of a huge African elephant.
And the solar arrays are massive. If you put the solar arrays at the toes of the Statue of Liberty, the other end of the arrays would come up to the Statue of Liberty's crown.
So not only are they big, these things are technological marvels. They are being bathed in radiation all the time, and they have to survive the entire mission like that.
Jupiter's radiation environment is intense, and Europa sits in the worst part of that environment.
Jupiter acts like a giant particle accelerator. There are charged particles trapped in Jupiter's magnetosphere that rotate with it. And these particles slam against Europa and will slam into our spacecraft as well.
We protect the spacecraft in 2 ways. Number 1, we try to minimize the amount of time we spend in there, which is why we are orbiting Jupiter and just flying by Europa. The second way we protect against the radiation is by having an electronics vault that we put our computer and some of the other sensitive electronics inside, which is made of about 1/3 of an inch of aluminum.
With each flyby of Europa, the outside surface of the spacecraft sees the equivalent of 1 million chest X-rays, just as we're flying by.
It's a pretty long trip to get to Jupiter from Earth, but not that bad from a planetary standpoint.
From launch to the time we get to Jupiter is about 5.5 years. And along the way, we have a flyby of Mars and then another flyby of Earth to get gravity assists to slingshot the spacecraft out to Jupiter.
I hope for the future explorers who are watching this at home that they take away from this that humanity, when we come together, can achieve really cool things.
This mission has been a long time coming, and we're so excited about what we're going to see when we get there.
We are in a golden age of robotic spaceflight exploration. How could you not be excited about something as monumental as this?
I am most excited about the potential to unlock the secrets of Europa, the potential to really understand this crazy world that exists and has likely existed in this condition for 4 billion years.
Now, of course, the scientists are very careful. They are saying we are not a life discovery mission. But when you know the kind of instruments they have, And when you know that the Cassini spacecraft at Saturn already found some similar evidence with less powerful instruments by looking at the plume of the little moon of Saturn, named Enceladus, it is very conceivable that we'll have extremely good evidence that will, of course, require another spacecraft, this time penetrating the icy crust, to go and see what kind of stuff is swimming in there. Now, I do not expect dolphins or whales or whatever, but certainly I would definitely accept some kind of bacteria. Yes, Anisham?
Yes, Dan. So in the video, they were saying it takes 5.5 years for Europa Clipper to actually get to Europa, and it launched this year. So we were looking at
2030.
2030. So we may have Chinese on the moon before we have a Europa around.
Yes, sir. That's the problem with a large scale of a solar system. It is not next door. And I remind you that we are supposed to launch the spacecraft on SLS. And it did not happen. Too bad, because then when you looked at the cost, it would cost $1 billion. Now, scientist missions don't have this kind of money typically. And so it was quite a good thing to reverse to Falcon Heavy. And by the way, Kristan and I prepared another presentation I put in the public domain, and I've sent a copy to you, about the launcher. Okay, now I would urge you to have a look, because Kristan reminded me when we were preparing this talk together, and then 67 slides is a little big. So what I did, I put most of those slides hidden. Okay, so if you want to dig in there, you will find probably something interesting. Good. So
basically, we had the same problem. Just talk SLS being way further. NASA has to get huge. Look at active contact. You have to do the contact.
sad but true.
And the sad thing was the SLS actually moved faster. It's a more powerful rocket.
Yeah.
But,
Okay, so
they don't actually have any available. I mean, they can only make one about every 2 years. They don't know how to mass produce them. Yeah, they're custom craft. And they needed it for artists. So they actually just couldn't do it.
okay, now it really started with our good friend Galileo Galilei here. He's on the right explaining to cardinals that he had found craters on the moon, phases of Venus, and that he had seen that 4 little dots were dancing around Jupiter. And of course, that got him in trouble. But he was doing this with very primitive instruments you see on the left. Those telescopes had been invented 2 years earlier by Hans Lippershey, a spectacle maker in Holland. And next to him is literally his neighbor in the city of, forget the city, but Mildenberg, I think, Middelburg, I think it was Middelburg. In the city of Middelburg, he had a neighbor, and this neighbor, Jensen, had invented the microscope. Well, guess what? Our Galileo got both. He got the telescope, he got the microscope. The guy must have been one of those guys like us, you know, who has to get the latest gizmo. Today, he would probably get the latest iPad. He would get probably to write his book using Chat GPS. He would be driving his electric vehicle while munching on a donut and drinking coffee, all that in Houston traffic. So that would be perfect. He would fit right in, you know. So anyway, the guy was very astute, and I used the Stellarium to check on his data. And Brooklyn, I want you to know this. Are you using Stellarium? That's a wonderful planetarium software, free of charge. The price is right. Highly recommend it. Stellarium is absolutely fantastic. Stellarium allows you to see the sky as God intended it. Okay, so you can see the constellations, you can see the planets, you can zoom on them. I have a little talk on my YouTube channel that I will share with you. so that at least someone has read it. It's fantastic stuff, absolutely fantastic stuff. What I did, I set the place to Padua, which is next to, with Venice, actually, even enough Padua. Venice, which is in the chromosome of the system, because it's close to Padua, where he was doing his observation in 1609. I set the date, okay? And I looked, yes, you can do that. And I looked night after night at what it would look like. And I checked on his book. And that's exactly what he said. Well, there are a couple of myths, because sometimes you have clads. My wife and I know that problem here. There is always, when you try to do a star party, always clads. Anyway, the guy just did a fantastic job with very primitive instruments you see on the left. These were 25 millimeter lenses. The best he had was 50 millimeters with a focal length of 1 meter roughly. And that would give him a power of 7 to 14. That's it. Now, 7 is barely enough. Oh man, binoculars are more powerful. But anyway, what is really remarkable is that he was able to do this with his very primitive instruments that suffered for horrendous chromatic aberration, for one. And he was able to do that night after night because he was curious. He was dreaming about the future. And that reminds me of Thomas Jefferson, by the way. He said, I prefer the dreams of the future to the history of the past. And so tonight, I keep dreaming. And that I think is pretty cool in a place like this to say that. So anyway, he was able to find those 4 moons that now we call the Galilean satellites. So what's the deal? Well, on the left here, you have Io, which is the most volcanic world in the solar system. Then you have, by the way, Io is about 5% bigger than our moon. Then you have Europa, which is 10% smaller than our moon. Then you have Ganymede, bigger than Mercury. You're talking about a very consequential moon here. And Callisto, which is about the size of Mercury, only 60 kilometers less. So this is the Galilean satellite for you. Now, Galileo could not understand the movement of those moons very well. He knew about their orbital period, but he wanted to have an idea of how far they were, and for that, he talked to his good buddy, Johannes Kepler. Now, Johannes Kepler was born in Germany, but he had to leave his native land in 1610 when he refused to convert to Catholicism. He ended up in Prague working for Tycho Brahe, probably the most astute and precise astronomer ever. Now, Tycho Brahe and his sister Sophie, by the way, put together an incredible compendium of data on the movement of planets. And they did this with protractors. That's what they had. When they were doing this job in the, let's say, 1470s, okay, there was no telescope. Remember, a telescope was invented in 1607. So they did this, but they did this so precisely that you can look at their ephemerides today. They are off by a minute or less than a minute of arc. Now that is quite remarkable. For instance, the moon is half a degree. Okay, this is 1 degree. 1 degree. The moon is half of that. Okay, so a minute of arc is a 60th of the, a 30th of the angle of the moon. That's quite remarkable that we were able to do this. So Kepler was able to look at the data of Tycho Brahe because Tycho Brahe had a good taste of dying the next year. Okay, so he had access to his treasure trove of data. And from that, and pure empiricism, he was able to derive the 3 laws that carry the name Kepler. So the first one is very important because again, you have in science to abstract your dearest illusions. And that's what he did, because everybody thought that the orbits had to be circular. The reason? Everything was created by God, and therefore, God being perfect, the creation was perfect. There is no more perfect than a circle, and therefore, all the orbits were circular. And that came from all the way back to Aristotle, okay, some 300 BCE. Now, what is really annoying about this is that there was a guy that was a little bit in the same kind of time, called Aristarchus, and Aristarchus had already decided that no, it was the sun that was at the center of it all. And when you have little data that is left after the burning of the Alexandria library, but we have evidence that he understood that there was an heliocentric model. And of course, it was unfortunate. It took some 1300s, 1450, for Copernicus to rediscover that. And he was very smart, however, smarter than Galileo. Before his death in 1543, he published his findings just before his death. Okay, so that he would be safe. Now, number one, the data showed clearly that the planets were in elliptical orbit, and that was obvious with Mars, because Mars has an eccentricity of 0.02, so all could tell that there was definitely something there that was not circular. Second, they sweep an equal area in an equal amount of time. Now that one is pretty tough to explain, so let me show you in a graph. The area A1 here is exactly identical to area A2 here, which means that perihelion, the whatever it is that is orbiting the sun, planet or satellite, is going faster tangentially than at apogee. And that is the kind of stuff we are still using today to compute the orbits of our satellites. Now, he was able to do this because he looked at the data and he tried all he could to analyze it with the tools he had. Now, he did not have logarithms. Okay, so logarithms were invented at about the same time, about 1610. The logarithms were invented at that time, but they were not ready for publication. Speaking of which, those guys, Galileo, Kepler, they were talking together. They were sending each other letters. We have those letters. We can see what was going on. And more importantly, the printing press had been invented in 1440, 1440. So they had books, and they would read each other's books. It's an exciting time to be alive by then. Amazing. And then the orbital angular speed is inversely proportional to the square of the distance to the sun. Oh my God, that's a mouthful. For that, of course, you may have to look at differential calculus, but this business of inversely proportional to the square of a distance was noticed by Isaac Newton. And indeed, the observation of Tycho Brahe, the Kepler rules were just empiricism. It would take one more century. It would take Isaac Newton and calculus to really explain all those things. And the last one is really the one that kills me. The square of the orbital period is proportional to the cube of a semi-major axis. How on earth could you determine that? He tried everything he could. He tried multiplication, multiplication, polynomials. Again, he did not have logarithms, but I'm sure he would have tried it. He tried trigonometry. He tried everything he could to find a relationship. Welcome to science. You have data, you try to fit it to a model. Okay, it doesn't work, no problem, you try again. That's like SpaceX. It goes kaboom, no problem, there is another one. So this is the way, I think, the best way to look at science. And on top of that, it's fun. Now, when you look at the data, it's pretty close. Indeed, when you look at the semi-major axis, and you cube that, and you look at the orbital period, and you square that, yeah, it's pretty cool, good enough for student work, don't you say? Now, this particular business is important to us at Europa because when you put the data into LogLog, this is what you get, a beautiful linear relationship. Of course, we are in LogLog for all the planets, but also for the moons of Jupiter. And that's what Galileo was after. He wanted to understand the relationship between the distances and the orbital period. However, he did not have the absolute measurement. Now that would take Newton, that would take another century, and that would take a better generation of telescopes to refine. But nevertheless, they had an idea already of a relationship between the orbital period and the semi-major axis, and that was already a big progress. All right, now to go back to the mission to Europa, this is what we have done. We have launched in October of 24. We are going to Mars, where we'll have a gravity assist on the 1st of March, go back to Earth on basically what will be pretty close to a Hohmann orbit, a Hohmann transfer orbit. We will arrive on the 3rd of December 26. And at that point, at long last, we will be on the way, going on the way to Jup. Now, arriving at Jup, we'll burn about 60% of the fuel for a burn of 8 hours to get captured by the big planet. So you're talking about a long trip, and you're talking about a lot of billiard game, gravity assist, to get there. Now, by the way, when you do a gravity assist in those particular missions, you do not burn at perigee, don't even try. It's just bending around, okay? And here is an example of what we did with Voyager 2. You have first the Jupiter flyby that really gave the spacecraft a good kick. I mean, at that point, it was hyperbolic. And then Saturn did pretty good too, but you will notice that the energy decreases a little bit because, of course, we are fighting the gravity of the sun. Okay? So you don't get a 100% free lunch here. And again, the only way that you can have an increase in the energy is by a change of direction. Because if you look at what's going on from the planet standpoint, you come with some kind of potential energy, your gravity transforms it in kinetic energy, but then you leave and the transformation goes back from kinetic to potential. There is no gain at all from the planet standpoint. But if a planet is moving, that's where the big difference is. That's where you can drag, if you like, into an increase. It's a vectorial composition. Okay, of the speed that you have, the tangential speed you have, and the speed of a planet. And it is this combination, this vectorial combination, that produces the delta V for free. But again, the spacecraft will not use its engines and use its fuel to do that. It's pure passive gravity assist.
So really, it's the movement of the planet that's importing the energy, and gravity is just what's connecting the spacecraft to the planet.
You got it.
So it's not really a gravity assist per se. It's really planetary movement assist.
It's a billiard ball. Okay, so basically, it's not like in a billiard when you have a shark, you know, but and it's more elastic. But yeah, it is the same idea. Imagine rubber bands, okay, instead of a brutal shock. So yeah, it is called gravity assist for that because you use the gravity of the planet to basically tug you along. Okay, yeah. And again, I don't dare to escape and go back to the slides. But if you look in the source of the PowerPoint, you will see a lot of poetry that I have waxed about gravity assist of all the math. But Christine reminded me that, well, why don't you put the math in hidden? And you were right. You were absolutely right. Okay, so this is what you're going to see when we arrive at Jup. The little dots here are the peri-Jove passage, so that's when we are closer to to the planet. And you have in red the very high dose of radiation. And I want to explain next why on earth it is so horrible to be at Jupiter, because indeed Jupiter is a hellish world. You know, our astronauts are protected from most of the radiation because we had the good sense of putting the space station under the under the radiation belts. But at Jupiter, we don't have a choice. We're going to have to go through it. And I want to explain next what the magnetic confinement that produces the tremendous radiation is about. So fasten your seatbelt.
First, magnetic charges tend to spiral around magnetic field lines, and the net travel of the charge tends to be along those field lines. Second, in a region where magnetic field lines are converging, there will be a component of magnetic force away from that region. This produces an effective magnetic mirror, which sends the charges spiraling back from whence they came. A simple magnetic bottle can be produced by two magnetic dipoles, shown here as two coils. The electric charges can be trapped in the region between these two coils.
That is that he had both electrons and positive ion in there, because they go in the different, where the force is different. Electrons, right hand rules. Positive ion, left hand.
A toroidal magnetic field can also trap charges by keeping the charges spiraling around the magnetic field lines. This is a simplified version of confinement used in plasma and nuclear fusion research projects like the International Thermonuclear Experimental Reactor. The Earth's dipole magnetic field can also provide a magnetic trap for electric charge. The charges spiral around the magnetic field lines, traveling north and south. The convergence of the magnetic field lines at the poles serves as magnetic mirrors. The net result is that the charges tend to be trapped in a band around the Earth, forming the Van Allen radiation belts.
Okay, so now you have it. Okay, this is the environment that we have on Earth that protects us from the solar wind that you described so well at the beginning of the talk. This is very important for the evolution of life. If we did not have that, we would not be here. Okay, because the radiation would kill us in a few minutes, actually. So you're talking about an extremely important part of the equation that gives us an opportunity for life. It's only the schnapps in all the elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. It's only those elements that is important. It's also the conditions under which you can have evolution on this planet. And so the magnetic field is extremely important. That's why life on Mars is very improbable, even within a few centimeters of the surface. If there is life, and I'm convinced there is actually, it's much deeper than that. It is much deeper than that. Because what do you need for life? I think the introduction clip was clear about that. You need a source of energy, you need water, and you need nutrients. You need organics. Okay? And we have all that on Europa that we know of. Now, the problem is radiation if you want to survive in this environment. And here, when you are at Europa, here, when you are at Europa, here we go. When you are at Europa, you have a radiation that would cool you in milliseconds. At Ganymede, you have a little bit more than 1 day. And even at Callisto, we will probably have colonies on Callisto when your children are ready to graduate from PhD. At that point, you may have some kind of colonies there, but it would kill you. It would kill you very quickly, because you would get the annual safe dose, which is 5 Roentgen equivalent. 5 rem equivalent in one day. Okay, a Roentgen equivalent man. Okay, Roentgen equivalent man. That's a cumulative zone. Okay, of that's cumulative unit of a kind of radiation you can accept. And the relationship, the regulations we have is that the total safe annual dose is 5 of these, 5 rem. Okay, well, you would get that in one day at Callisto. So that still poses a tremendous challenge of engineering, of making sure that you reduce radiation even at Callisto. So anyway, this is a pretty nasty environment. And when you have worked in electronics like I did, I shiver at the idea of having to build a system like Europa Clipper, knowing it's going to such an environment. What they did is that they put all the electronics in a vault of 1 centimeter of titanium, and typically 1 centimeter of aluminum, 1 centimeter of titanium is enough to make the hard-drive system survive that. But you have dual redundant 1750As computers. We have FPGAs that are triple redundant. I mean, the electronics engineers who did this know their stuff, okay? And you need that, because we had the same problem with Juno, who has the same kind of an issue, trying to get to Jupiter in this case, but getting the heck out of there into a very elliptical orbit, and coming back, getting the data, and then getting out of there as soon as you can. We'll do the same thing at Europa. The JUICE spacecraft, the Jupiter Icy Moon spacecraft of the European Space Agency, really is gutsy, because they are going in orbit. They are going in orbit around Ganymede. And that is itself quite a challenge. And so for that reason, they have twice the area of the solar panel that we have, because they know the solar panels are going to get it on the chin. And they have also a vault. I mean, there are all sorts of, I wish them good luck, because there is a tremendous amount of bad stuff that can happen at Ganymede. Now, let's compare that to the Earth. Okay? In the Earth, we have something like 50 microtesla of magnetic field. A moment that you see at the very bottom here. Not very important to look at those numbers, but I want to simply make the point that even though the magnetosphere of the Earth is about 7 times the radius of our planet, at Jupiter it's 100, the radius of Jupiter. Okay, so there can be 7 million kilometers of radius, and then the magnetic moment of the planet is 20,000 that of Earth, and that means that the magnetosphere of Jupiter goes all the way nearly to Saturn. When you're talking about a pretty big magnet here, a pretty big magnet that all the way to Saturn. Yes, sir. So you're talking about from 5 AU to 9 astronomical units. You're talking about the mother of all magnetosphere. But that is just because not only has Jupiter a very active dynamo because of the liquid hydrogen, basically the metallic hydrogen, which allows the current to circulate, but Jupiter is compounded by the Io torus. You see, Io, the inside moon, is constantly malaxed, back and forth between the gravity of the planet and the gravity of its sister moon. I'm not sure I specifically said that, but the free inside moon of Jupiter and resonant orbit, when Io goes for 1.75 days orbital period, Europa goes 3.5 days, double. And Ganymede, 7 days, double again. So it is this resonant frequency and this constant flexing back and forth that produces the tremendous heat that makes Io the most volcanic world in the solar system. Io is constantly turning itself inside out, constantly. But it spews in the cosmos some geyser of basically SO2 and other compounds that produce a torus that is ionized and produce itself a 3 million amp current, 3 million ampere current. Now, at Earth, we do not have that. At Earth, we only have to deal with the CMEs and with the solar wind. But at Jup, you have a very complex interaction between the current in Io torus and the current generated by the magnetosphere of Jupiter. So that's why it is so unbelievably big, and that's why it's such a nightmare to have to fly in this environment. Now, the spacecraft is huge. Basically, its length compares to the length of a basketball court. And it produced 300 watts at the beginning of mission. 300 watts in those big panels. We will have 49 passes at Europa. Make me sure I'm not forgetting something. And in those 49 passes, we will be able to image about 65% of the area. 65% of the area of the moon. Okay? So if you look at the instruments we have, I believe this is the most comprehensive, the most impressive set of instruments I've ever seen in my life. Of course, I worked on Landsat, I had a small stint on Cassini, but this is really, this is a flagship mission, okay? It's a $1 billion mission. The flagship missions are always the best and greatest, and they have overdone themselves this time. In particular, I will only cover two. Thanks to you. I limited myself to two instruments, okay? The magnetometer and the mass spectrometer. And these two instruments by itself will allow us to determine a lot of what we have to know to determine whether or not we have life on Europa. However, as the scientists remind us, extraordinary claims require extraordinary proof. Okay? And so they will not tell you, oh yeah, we're going to find life. But by what I've seen, I think at the end of a mission, they will have a pretty good idea. Yeah, we've got to go back. And this time we have to penetrate the ice and have a look inside, see what they look like, those fish in Europe. Okay. So we have basically a set of instruments that do remote sensing, like we do on Earth for a living. Ultraviolet and infrared is a pretty good way to have a look at the hotspot to see if it's conceivable that some warmer water is jutting out from the inside. But we can do a tremendous amount with just gravity. Radar in particular, and that's why I will cover reason a little bit. The radar that we have will allow us to see the elevation in the terrain. And if you have, for instance, icebergs, and on Earth, icebergs have a bad tendencies to flip. So if you see a flip, you will know there is an iceberg. And not only that, but you will be able to see the height of the flip. And from that, determine the height of the iceberg itself. And from that, the where the ocean probably is underneath.
How big is the ice supposed to be?
Great question. We don't know for sure. We don't know for sure, but they are betting on 30 kilometers.
And an iceberg that will flip when it's 30?
Well, that would probably be a domino effect, okay? But there would be some kind of gravity change, okay? And that will be seen by the radar. But you're right. Typically, what you would see if it is an iceberg, as I said, then it would probably be a patch, a little reservoir of water there in the middle, okay, because you cannot have 30 kilometers going all the way. But, you know, it is very exciting to see this set of instruments that they have. Infrared is a big deal. The gravity is another. The radar is which is why the JUICE spacecraft has a leader. Okay, at Ganymede we will have a leader, and also JUICE will pass through Europa a couple of times, and the leader, I hope, will be used as well, because it will help calibrate the data we have from the other spacecraft. And that is so exciting, is that we have two spacecraft going to this system at the same time, and they will be able to cross-calibrate each other. And certainly in the case of Europa Clipper, they have a most impressive suite. And of course, in situ analysis, even though in situ is a little bit optimistic, but because we are not on the ground, okay? Nevertheless, through a mass spectrometer, the surface and dust analysis, SUDA, which will look at basically what comes out when a micrometeoroid hits the surface of Europa, poof, some stuff comes out. What does that look like? You know, that's what we're going to do with SUDA. The magnetometry, which I'll cover in a moment. The Faraday Clubs, which is just looking at, it's an electroscope, basically. It's looking at the charges. It's looking at the charges, and it will allow us to study the exosphere, the atmosphere, if you like, of Europa, including the total electron count, which is important for all sorts of reasons. Then gravity, of course. So this set of instruments is unprecedented. We have never had this kind of precision before. And we do all that on the basis of one flight, Galileo. And Galileo was launched when I was still at Goddard. And in '96, it discovered this disturbance in the magnetic field of Jupiter. It could not be anything but a liquid ocean. But that's the only thing we have. So we do not know really how thick the ice is. And unfortunately, the latest papers I saw indicate that we may be wrong about this, that the depth of this ice can be 60, 70 kilometers, at which point we will not be able to see the what we were expecting from the radar, because we have an ice penetrating radar, but it goes all the way to 30 kilometers at best. So if it is 60 kilometers, we will never know. That's the way science works. So the most important instrument for this particular business, there are two really, the magnetometer and the radar. But the magnetometer also is quite interesting. I mean, it's Fluxgate magnetometer. I have all sorts of poetry I wax about Fluxgate and the electronics that goes with it. If you open the PowerPoint. But basically, we are trying to look at the magnetic field at Jupiter in 3D. Okay? And we have those particular sensors that are as far as we can from the spacecraft. So the spacecraft has all that electronics and those cables and current is going through it. A lot of magnetic field is generated by the spacecraft. So you want to make sure that you are not spitting in the air claiming it's raining. Okay? You want to make sure that you shield yourself from this electric field, electromagnetic field, that is not the magnetic field of the planet or the magnetic field around Europa, but your own magnetic field. And so for that, we have 3 sensors that are at different positions on the boom. And at 8.5 meters, by the way, you basically attenuate the impact of magnetic field generated by spacecraft by a factor of 600 compared to the emission. Okay? And the reason for that is that the magnetic field decreases as the cube of a distance. So cube 8, it's about 512 actually. The cube of 8 is 512. But the cube of f.5 is about 600. So you're talking about a 600 attenuation by the sources from the spacecraft. And of course, when they tested the spacecraft, they were very careful to putting the instruments to limit this particular effect. So what we'll be able to see with magnetometers is ocean depth and thickness, because basically the ice is a very poor conductor of electricity. But water, particularly salty water, conducts extremely well. So it is this difference that will allow us to appreciate and perhaps determine the depth of the, it's a little bit too difficult to explain, but basically we are going to look at the variation of the magnetic field. And this variation of the magnetic field, imagine it is a variable signal. This variation of the magnetic field, the period of it will be several days and months. And the reason for that is that there is a variation of the magnetic field with a synodic period of Europa. That means when Europa comes back at the same place vis-à-vis Jupiter, okay, there is a variation of the magnetic field due to that. And there is also a variation of the magnetic field due to the orbital period of Europa, which is 3.5 days. Okay? So all those things will give you a Fourier transform at the end, but with a period that you're looking at months. And that means that the spacecraft will have to go around and be very patient, collecting this magnetic data to ferret out this signal, the period of which can be several months. And it is through this that we can determine the depth, because there is a rule called the Hoffman rules that basically the conductor, the field inside a conductor vary as the inverse of the square of the depth of it. And it is through this data they will be able to determine the depth of the ice layer. A little bit too much, I'm sorry. But if you open the PPTX, you will see some poetry waxed about that too. Right? It also depends on the conductivity. So a lot of salt in the water will allow you, of course, to conduct the electricity faster. And each sensor has a very, very large bandwidth. We have 4,000 nanotesla, that's huge, with a 1.5 nanotesla accuracy. The variation we expect is about 20 nanotesla for the orbital period. And the strongest signal is the synodic period, as I tried to explain, but this one will be much bigger. But that means that you're going to have to calibrate this thing. And there are several passes that are designed in the plan, the flight plan, to calibrate the magnetometer. But that also means that you have to keep the magnetometer happy, and you have to regulate its temperature to within 1 degree. Here is the way it looks. I just wanted to have a look at real flight hardware because of my audience. And you will see that it's pretty sophisticated right there, just this little sensor. Not only do you have a course of a flux gate, but you have to take care of radiation. You have to take care of maintaining the temperature. That's a pretty impressive piece of engineering right there. And here I have another little clip that shows you the deployment of a magnetic boom. Now, this occurred last month. Okay, so that's red hot off the press. Now, this is a simulation. This is a simulation, but this event occurred last month. So the good news is we now have deployed the magnetic boom, and that is important because we learned that lesson with Galileo. Galileo had a beautiful high-band, high-gain antenna, and we were planning to deploy it, but again, Congress had redesigned the mission for us. And instead of being able to straight go to Jupiter, we had to go gravity assist to Venus. So a spacecraft designed to go in the frigid outer space now had to go closer to the sun. And that destroyed the lubricant that we had in this antenna. So the antenna never deployed. It deployed half of it. And then I remember that very well because I was part of the Tiger team. We had to really do the best we could to compress the data from the spacecraft. Unfortunately, we lived in a time when we had computers and relatively good processors on board. certainly better than the SSC1, which was a PDP-8. We had better processors on board to do this very complex compression algorithm, and that's what saved the mission. But we know that it's pretty hard to deploy stuff in space. Space is hard. Okay. Anyway, the other instruments I want to cover, but I will go quickly because I'm running out of time, is the radar. And surprisingly, the radar can penetrate the ice pretty nicely. And we'll use that as reflectometry to see how rough the terrain really is. And that's where my business with the ice cubes will come into play, because that will show on the radar. We expect a 3 kilometer resolution at 30 km. We'll also have a total electron contents plasma characterization. And we have 2 frequencies. Now that's a leg up on the JUICE, because JUICE only uses the 9 megahertz 33 meter radar. They have 2. A lower frequency allows deeper penetration. Higher frequency gives you better resolution of the ground. Next, I want to tell you about what I consider is the jewel of all spacecraft instruments ever flown, the mass spectrometer. That brings tears to your eyes. The way they designed this thing is astonishing. First, they want to have a look at not only the ions that we will sniff at just in orbit, but also have a look at what is coming out. As I explained before, the micrometer wave and all that, there is all sorts of ions that will come and will be sniffed, literally, by the mass spectrometer. And basically, this mass spectrometer consists of a little bottle that will cool down the sample so that they are all at about the same kinetic energy. That's very important. When you want to do mass spectrometry, you have to start with a similar energy, because what you're going to do next is make those ions go back and forth between 2 mirrors. This time it's not magnetic, it's electric. But we're going to have to go back and forth. And the reason for that is that the very small and fast ion will go faster and will be separated from the fatso. The fatsos will go much slower. Now, what they have done that is beautiful, they have done a system, they have put together a system of reflector by which you do that several times. So instead of having 1 turn around, you do 200 times around. And by that time, the little guys have gone much further out, and the fatso are still further down, and you can have a much better resolution in the mass that you get. Ionize here, blah, 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 blah. Let me keep that. But it is an absolutely magnificent detector that we have never had such a precision in instruments like that. And that is so much above and beyond what we had on Cassini. And even on Cassini, we were able to tell, yeah, Enceladus as organics. And we could see that we had really pardon my French, yeah, we had pretty big molecules. Okay? We had pretty big molecules just with a very simple instrument we had on Cassini. So with this thing, my God, and here, you know, I decided to dream a little bit. I say, okay, let's take the simplest amino acid I know of. It's leucine. Okay? It is the simplest amino acid, major component of proteins. And already you see that we have the COOH here, the carboxyl group. That means it's an acid. It is an acid, right there. COOH. Remember acetic acid? CH3COOH. CH3COOH. That's vinegar. Okay? So this particular thing says it's an acid. Then you have a methyl group, CH3COOH. You have a CH3 group, which is very common in organic chemistry. You see that everywhere. And you have the amine group. That's what is called an amino acid. So this is the simplest amino acid, the simple brick of the proteins of life that we have. Well, it may be simple, but when you look at the spectrum, you get that. So I'm talking about the simplest amino acid. And you're taking a very impressive set of masses versus charge that you have then to deconvolute, because you will not have only one. Let's assume that I throw a bacteria here. Oh my God, you're going to have a forest of peaks, and you will have to deconvolute all that to try to ferret out what could produce this complex signal. So we may have a wonderful instrument, but what will make the difference is, of course, the processing and the arguing that will ensue. The surface dust analyzer works in a little bit along the same way. It's a time of flight. That means the fat ion, again, will take much more time to go back to the detector. Then I will go very quickly to the other instruments, which are the UV light, the visual experiment. The visual is very good. You have, as usual, wide angle and a narrow angle. But on top of that, the camera is equipped with a stereo detector, so you can have stereoscopy. And the mirrors are gimbaling into angles, so you can go off track. So this camera will produce very beautiful pictures. And this is the UV. These are these are the plasma instrument, but this is basically an electrometer, again, looking at the amount of charge. So we are talking about very impressive spacecraft. The attitude control system is capable of maintaining something like a few arcseconds. It is made, as usual, of magnetic wheels and thrusters. The redundant IMUs, the works. Okay. Now the European, which I did not have time to cover, of course, is equally impressive. Again, what makes a big difference here is the leader, as I described. But we are talking about two extraordinary spacecraft going at the same time in the same area. And that's why I was dreaming of having those guys awarded the Nobel Prize. Because if they found life, it will not be with this mission, no. Because there will always be people who will say, nah. And for instance, you may remember ILH 84001. Let me consult my notes that I don't tell you some stupid thing, but I think this thing was ejected from Mars some 17 million years ago. And it arrived on Earth some 13,000 years ago. Come on, Denro, you can do it. And people said, oh, that's it, we have found life. Yeah, that's it. We have found life. Well, the trouble is, indeed, we had magnetite. We had polycyclic organics. We had some globules that look like sulfate and carbonates. And we had a little fossil that looked like a nanobacteria. Little itsy-bitsy bacteria. Oh, so cute. Oh. The problem is when you looked a little bit closer, I said, no. All that stuff can be simulated by interaction of rocks with hot water. Hydrothermal vents. Hey, I like that. Okay? Hydrothermal vents on Earth are extremely productive. I will be happy to see that. But no matter what you do, people will shoot holes in it, and that's the way science works. And that's the way it should be. Now, the dream is on hold when it comes to LH 84001. But some dreams die hard. And in particular, this dream of finding life on another world will never end. Now, when I worked at the Goddard Space Flight Center, I had my share of beautiful dreams ruined by ugly facts. But I cannot find a better way to terminate, to end my talk, but to quote Dr. Goddard. It's hard to say what's impossible, for the dreams of yesterday are the hopes of today, and the reality of tomorrow. Ad Astra.
Thank you so much, man. I really appreciate it. I guess, do you have a James Webb Telescope calendar?
Not in my house, no.
No, but I think we should change that. What do you think, Doug?
Yeah, sure.
So this is from Doug. And so whenever you see it all year long, hopefully you'll remember us and come up here and
thank you. Appreciate
talk to us. Thank you so much.
All right.
Well, guys, I think we're going to end the meeting here, and then we'll pick it back up over at PJ's, where we'll figure out what we're going to do about, Christian, I guess you'll be able to talk to us about your plans for the Science Engineer Fair of Houston and how we could help and I guess we're going to have a booth up there. I think Robert has some ideas around that. So anyway, thank you all so much. See you all soon. Oh, and can we take a group picture real quick? So if you're still online, maybe you could turn on your camera and we could just take a quick group picture. That would be awesome. Maybe I get everybody up here real quick.
Should we move the table out of?
Yes. You want to get that side? And watch out for the cords. Oh, let's go this way. There's more space. Otherwise, we have the podium. Oh yeah, if I could just get everybody take a quick picture. I want you in it. I want you in it. I'll do it. No? Oh, okay. Oh, fine. Would y'all mind taking a picture then? Oh, well. Anyway, everybody all together. Yeah, I know. Oh, you can take the picture? That's
unless you prefer a selfie.
No, I don't. Thank you. Okay. Everybody, what's your name?
Marisha, I need
Marisha?
further in, and I need the short folks in front.
Excellent. You've done this before. Short.
I need the shorter folks in front. All right. Would you guys? Yeah, we still have some gaps here. Could maybe a couple of you guys move over to this side of the back or something like that? We've got gaps here.
Okay.
Yeah, I'm only 12. We still have 12. Maybe some back.
Maybe in back, Robert.
I want you to lead.
We still need to rearrange some people's spaces are. Let's see. I know we want our speaker there. I'm sorry, the lady with the hair. You're blocking the gentleman. Yeah, you're blocking his hair. So could maybe your daughter squat in front with them? No, I mean, well, it's I'm just okay. All right, that's fine. You guys want the screen in back? Okay. Thank you.
That is brilliant. Thank you so much. I think that may be our best group picture yet. Thank you so much. Okay, bye, JR. Bye, everyone. Oh, I'll let you close this down. I'll get this back to you.
Turn off recording and everything. Okay. Where's the other one? You have the other one, or? Well, there's two. Where's the third one? Ah, okay. Good, thank you.
Now I understand.